Okay, folks, we're here on the 9th. We're going to be looking at 4.2. Just keep in mind that the drop grade, the final drop date is tomorrow. I'm not encouraging anybody to do that, but you're going to need to decide by looking at the grades in the grade book of Canvas. The Canvas grade book is where the grades should be accurate. So after every due date, they're pulled over, and I went in and made sure everything was right this weekend. So that should be pretty much accurate. If you're missing a test grade, you're going to get to make that up with the final exam. So that could raise up your grade considerably. So just keep all that in mind as you're doing all this. All right, before we get going, has anybody got any questions? All right, I assume y'all are hearing me okay, right?
Yes.
All right. All right, so we're going to look at 4.2 today. We're on our way through chapter 4, and we're about a little over less than halfway. And once we finish that, we'll have our final regular chapter test on all of chapter 4 this time. And then planning on getting that all done before Thanksgiving so you can forget about things for a day or two. One thing I might just bring up, if you got any Wednesday classes, you got to check with your teacher, because that was one of the days they kind of took away, but it could be optional. I've heard varied things on my Monday, Wednesday class. I'm going to do everything I can to make sure we're ahead so that we don't have to work on that day, because I really, know that people need time to get prepared for Thanksgiving. So just keep that in mind. It doesn't, but for us, of course, there is no class on Thanksgiving. Yeah, and just like I said, is and I saw a question here. The My Math Lab is just for the assignments. It has nothing to do with the grades. The grades are not accurate over there. So the Canvas contains, the grades, because we're supposed to be using Canvas. So I do everything in Canvas and make sure everything is encoded well there. And you can even see what I'm showing you here now. You see all the percentages, like the homework is 10%, the My Math Lab quiz is at 10%, the tests are 25%, the midterm is 25%, and then the exam is going to be 35%. And plus, it'll take up any, oops, I'm showing grades, I shouldn't be doing that. Anyway, sorry. Just keep in mind that that's not accurate over there, okay? The My Math Lab. I just copied the way it's set up, and that, since the grading is different, maybe it'll be different over there. I didn't even look at it. I pull the grades over into Canvas, and when we reach the due date, then that's what we, it should be accurate. Because they've got a grade book over there too, but like I said, we're not using that one. All right. So 4.2, we'll go through this little presentation, and then we'll work through some other problems from the back of the book. All right, so chapter 4, section 2 is about logarithmic functions. And logarithms are the opposite, or I guess you could say the reciprocal function or the inverse operation of exponential functions. So they undo one another, like multiplication and division, addition and subtraction. Okay. Now, since they are inverse operations, we should be able to take logarithms and change them to exponents and exponents to logarithms. We should be able to evaluate logarithms and then use basic logarithmic properties. We should be able to graph to a certain extent, find the domain. Again, that's looking at the x values. Now, what's going to change with the logarithmic functions, and this is one of the few times that this happens, functions generally are going to be domain of negative infinity to infinity, or all real numbers. Here it changes slightly because of the input of a logarithmic function is limited. All right. Oops. And there's two kinds of logarithms. Well, there's actually any number of bases on the logarithm. The common logarithm is what we call base 10. And natural logarithms, which are very much related to things that happen in nature. All right, so here's the relationship between a logarithm and an exponent. All right. Let's try to make sure I got everybody's here. I got everybody. All right, so a logarithm, and we're using y here just to kind of make it more simplistic, but that's kind of can be replaced with f of x. The log of base bx is the same thing as the base raised to an exponent that's going to be equaling what's inside of the logarithm. So essentially, I guess a simplistic way of putting it is the answer to the logarithm is the exponent, the power. All right, you're given the base and you're given the outcome of the exponent, and then it's up to you to determine what power would give us that. So that means then that if we have one, log 7 of x is equal to 3. Well, that just means that 7 to the third power would be equal to x, okay? 2 equal to logarithm b 25 means that b is the base, b to the second power is equal to 25. So when you're evaluating an logarithm, you're looking for the power. Logarithm 426 is equal to y. When it sits all by itself on the other side of the equal sign is what should be the power. So in this case, 4 to the y is equal to 26. We're not asked to evaluate this, but what we're doing is just showing the relationship between logarithms and exponents. All right, so now going the other way. If we got 2 to the 5th power is equal to x, well, we've got the two things that we need here to build the logarithm. The power is going to go by itself on one side of the equal sign, and knowing the base, the log of 2, base 2, x, because we don't know what that is, then let's go in there. b cubed is equal to 27. So the base b, so that means log b, and then the 27 goes with the logarithm, and that's equal to 3. All right, this is that thing called the natural, the e, that's the one they call the natural. The logarithm is its counterpart. So log base e, and generally speaking, what they'll do is they'll say L of n is the, rather than say log of e, they'll say L of n, meaning that's the natural logarithm. So e to the y is equal to 33. So we don't know what the power is, so y is equal to log e 33. Okay. All right, so we've got two things here we want to evaluate. They're both logarithms, so we got to find out what does 10 to what power, or 10 to what power gives us 100. And then this one is 5 to what power gives us 1 over 25. Okay, so log 10 of 100 means 10 to what power gives us 100. So therefore 10 squared. So we need to have 2. 2 is the evaluation part. That's where we're finding out what we need, or essentially the answer. 10 here to this, to what power? 2 power gives us 100. All right, this other one is 5 to what power gives us 1 over 25. Now, since we're going from a base of a whole number 5 to a fraction, essentially, then it's going to have to be a negative power. And we could hopefully also know that 5 times 5 is 25. 25 times 5 is 125. So we need two things. We need the 3, and then we need a negative sign to give us the reciprocal. Remember, the negative sign in the power or the exponent means we take the reciprocal. All right. All right, here's another one. Log base 36 gives us 6. So now notice what's happening here. We need to go from a base of 36 to a smaller number. So that means we're going to have a fractional exponent, or what's called a rational exponent, actually. So what does that? Well, the square root of 36 is 6. But remember, the square root can be expressed as a rational exponent. Can be expressed as a rational exponent. In other words, a fractional exponent. So 36 to the 1/2 is equal to 6. And that means the same thing as the square root of 36. So let me just show you this in case you don't remember this. So this is a 1/2, just a very bad one. All right, and then the general rule is, let's see, the nth root of x is equal to x to the 1 over n. All right. And then you can also do it as in this way too. We probably won't need this now, but I'll just refresh it while we're at it. All right. So this is the one we're looking at now, but I think we're later on we'll be getting that one when we're getting a little bit more on exponents and stuff. All right, now here's one we're asking essentially what power of 3 is going to give us the 7th root of 3. Well, we're just going essentially back to this thing here, because what we have is we have this here. And remember, so if we have the 7th root of x, that's x to the 1/7, okay? So that's what's going on here. So what power gives us that? Well, it's 1/7, because 3 to the 1/7 would give us the 7th root of 3. Now this one doesn't simplify out to anything, so that's just why it just stays as the 7th root of 3. But that's what it means. All right, log base b of b is equal to 1, because anything raised to the first power essentially just gives you back that base. All right. In other words, we'll see it in an example, but anything raised to the first power, it just ends up being that same base. And anything to the 0 power is equal to 1. All right, that's what they tell us in here on this one. This was b to the first power, well, it's just equal to b. But 0 as an exponent will just give us 1 for any power. I mean, for any exponent. All right, so here's 1. 9 to what power gives us 9? Well, it's 9 to the first power. 9 to the first power is just equal to 9. Generally, you know, you won't see something like this written. You'll just see a 9. So it's hopefully just understood that if you have any base, it's just going to be, and it's raised to the first power, it just means that it's that same base. All right, and then if, what do we have to do to the base of 8 to get 1? Well, we raise it to the 0 power. And that applies to anything. Doesn't matter what it is. Same thing over here. You know, x to the first power is equal to just plain old x. And then the inverse properties of logarithms. If we have a b that's greater than 0, base greater than 0, and it's not equal to 1, then what this essentially means is that these b's undo one another. If you raise a base to b to any power, then you essentially just have that power. Likewise, if you take a base and raise it to the same log base of a particular value, then these two things essentially undo each other and you just have the x. They essentially mean the same thing. They're just going backwards from their own perspective of whether it's a logarithm or an exponent. Okay, all okay? All right, so here, what's going to happen is log 7 or log base 7 of 7 to the 8th power. Well, this is simply just undo one another, and the 8 is left over. Likewise, if we do it from the logarithm side, base raised to the log of bx, these two undo one another, and we're just left with x. So if we take 3 base and raise it to the log base 3, 17, then it's equal to 17. All right, well, the graphing, you know, we looked at it for exponents, and it works the same way over here. because the logarithmic function is very similar. You remember how inverse functions work? So watch what happens with this one. And we're going to just evaluate a few of these. When I go through one, we'll just we'll try to do 5 points just so we have 0 and then also a 2 or something. And you got to just realize, especially with an exponent, they get big pretty quick. All right, so we had done this over in the last section, but if we have 3 to the x power, then if we use -2, remember negative means reciprocal and then square it, so 1/9. -1 means 3 to the -1, so it's just the reciprocal, nothing done to the 3. 3 to the 0 power is just 1. Again, remember how all exponents go through that value, 0, 1, and then 1. If the exponent is equal to 1, 3 to the first power is just 3. All right, so now watch this. Then this is what makes it kind of easy to evaluate these, because of the fact that, remember, these things are inverses of one another. All right, so we really don't have to do any more evaluations. We're essentially just going to swap spots. In other words, the x, remember how we did those inverse functions, how we just swapped? Of course, that may have been 130, but in order to find an inverse function, you just swap your x and y, and then you solve for y again, and that gives you the inverse function. Well, this is what this is, except they're doing it, we know. It's just a matter of, now we know that to get the points, we just have to flip-flop them. In other words, the x is -2, -1, 0, and 1. The y, or the f of y, is 1, 9, 1/3, 1, and 3. We just looked at those. So then what's going to happen with the inverse logarithm is this, the 1/9 is the x, and the functional value is -2. 1/3 gives us 1. 1 gives us 0. See how it's just backwards from this one. 3 gives us 1. So when we graph them, look at that. These things are symmetric. And it's symmetric by across the line y is equal to x. All right, so they're just going to be opposites of one another. And as I had said here, here's the 0, 1 that all exponents go through. And notice that the inverse would be 1, 0 over here. So all logarithms are going to go through that. All basic logarithms, just like all the exponential functions basic go through that. If it's got a shift, then it'll move whatever many is in the x or the y. So see that? I mean, that's the basic logarithmic function. It doesn't matter what the base is, it'll be very similar, and it'll always go through this one. So then the logarithmic function will do the opposite. All right, and now let's look at this before we go to that page where we talk about the domain and range. Notice that on the red, which is the logarithmic function, that it has this vertical asymptote at x equals to 0. X equal to 0. In other words, on that left side, this thing goes down and it's going to hug very close to x equal to 0, or the y-axis, but it will never get there. So the smallest that it will ever be will be 0 parentheses wise. It won't ever get to 0. So we would have 0 parentheses on the left side, and this side is just going to keep on going and going and going and going into infinity. Now remember, we talked about how most all functions are going to be negative infinity and infinity, and you can see on this side how this is headed way, way out west, to negative infinity, and it's going up, and it's just going to eventually cover up all the x-axis as well, because it's not going straight up, it's going, you know, on an angle there. So that's why with the exponential function, it's negative infinity to infinity, all real numbers. But on the logarithm, there's going to be an endpoint. And in this case, for the basic one, it's x. It can't be x equal to 0. So 0 would be the smallest it would ever be, and it would have a parentheses there. So here we go. So for the basic logarithmic function, all real numbers in the domain of 0 to infinity, the range of f of x is equal to all real numbers now. Again, you can see that for the range, if we're just looking for y, ignore the x-axis. If you're willing to print this out and just erase the x-axis, then you could turn it essentially, you know, 90 degrees and see that this thing's going down to negative infinity and this one's going up eventually to positive infinity. So that's why the range now becomes all real numbers, because this one's the one that's limited. All logarithmic functions are going to go through 1, 0, all basic ones, because remember, the counterpart, the inverse function, goes through 0, 1. And therefore, there's no y-intercept. It's never going to get to that y-intercept because that's x equal to 0. So for b is greater than 1, in other words, the base is greater than 1, the graph goes up to the right and increases. Now, if it has a fractional, then what's going to happen is it's going to be a decreasing function. Let me just kind of show you what that means. I always like a nice visual myself. We looked at the exponential function and how it changes when we've got a fractional. All right, so well, let's just say we got 8 3/4. It's a fractional as in less than 1. Let's see how it swapped around. All right. Now, if we did this with oh, I should have done this. Okay. All right, so let's look at the logarithmic one. Let's see, there's a thing here. We got to put oh, I know what it is. I can't write out log. I got to use this. Let's see. All right, well, that's probably terrible. Well, it's back. I guess I shouldn't have tried that because I just wanted to illustrate this fact. You remember, you saw how it does on the exponent, how it flips when it's a fraction. Well, the same thing kind of happens. It goes down and to the right. And that is what's going on there. Okay, it's just that this one is not the inverse. Well, I'm just going to be spontaneous. There's probably not the best idea. And then as the graph of f of x is equal to log b of x approaches but not touch the y-axis, the y-axis where y is equal to x is equal to 0 is the vertical asymptote, as I pointed out. All right. See, there's that vertical asymptote. So the domain of all logarithmic functions is that it's got to be, the domain has to be greater than 0. All right. Now, if there's a shift, then of course it changes, but that's essentially what that means. So let's say if we want to find the domain of something like this. All right. F of x is equal to log 4 of x minus 5. Well, since this part right here has to be greater than 0, it's very similar to how you're dealing with a fraction. And if you have a fraction that has a binomial, or even if it has a variable in there, just plain x, that x in the denominator can't be 0. So if we had x minus 5 in the denominator of a function, then what we are stuck with is the fact that x can't be 0, or x minus 5, and we had that down there, can't be 0. Well, it's the same thing here with the logarithm. All right. Remember, this is the base, and this is the outcome. So x minus 5 greater than 0 means that x has to be greater than 5. So this requires a shift. Remember, the shift from left to right. Then let's see if I can manage that. And what it was that x. Right. See how it shifts now, and 5 becomes the x asymptote. All right. I'll say the other way, let's say. So see, it shifts. Now -4 is. So in the basic logarithm, that it has to be greater than 0. But if there's a shift caused by, this is what we call the, the left to right shift, the horizontal shift, then that domain will change based upon what that is, solve for 0. In other words, take it and solve it for greater than 0. It has to be greater than 0, so 5 becomes the new thing. And so that's what I just showed you. So everything gets changed over. It still goes through through basically the same shape. Everything is just shifted over to the right 5. All right, the logarithmic function with base 10 is called the common logarithm function. That's the one that's telling you that's the most popular. And calculators, when you see a calculator, here, and we see, where is it at? Logarithm. Oops, let's just say that means base 10. So in other words, let's say if we had 25 log, then we get 10. So let's do this. Let's see, that's the base 10. Anyway, the other one, the one we'll be looking at, is the ln. Like I said, there's no on here, if there is on most calculators, are not going to have the other bases. So there might be a way to input them, but it depends on the calculator. I don't think you're going to need that though, as far as I've seen. All right. So log base 10, when you see just plain old log, that's what it means. It means base 10. You usually won't see the base. Just like when you see ln of x, that means log base e. All right, let's look at a couple of applications, and then, like I said, we'll go through some of the things in the back of the book. The percentage of adult height attained by a boy who is X years old can be modeled by f of x is equal to 29 plus 48.8 log of x plus 1, where x represents the boy's age from 5 to 15. All right, so x has got the restriction there from 5 to 15, and f of x represents the percentage of his adult height. So once we put in a value of x and evaluate, that's going to tell you the percentage of his adult height. All right, so let's just say we wanted to find out what percentage of an adult of a child's adult height has a boy attained at age 10. All right, so what we do is we put 10 in for x, using that. That's the same right there, the one that was up there, 10 plus 1, so that means log of 11. So let me just show you how to evaluate this, and usually on most calculators, you kind of gotta work a specific way. Now, the optimal thing to do is to write these down. In other words, what I would do is take 11, put it in, and take the logarithm of it. All right. Now, the 48.8 is multiplying that. So I would write that down and make sure you go out a few more decimals. All right. They're going out to just whole numbers, but always go. This is just general mathematics, rounding off things. Always, if you ask to round off to a specific decimal place in your calculations, you always want to go a couple beyond that, because of the fact that if you round off immediately, then you're losing accuracy that you will never be able to recover without doing the calculation again. So what you want to do is always go a few beyond, decimal places beyond what you're going to round off to, and don't round off until the very end to the particular decimal place, okay? So anyway, so I would write that down and maybe go out to about right there. And then I would take that and multiply times 48.8. So that gives us 50.819, or and then we're going to add 28.9 to it. So then that's 79.82. So that's why they rounded off to 80%. They asked for this percent. They didn't say out to a decimal place. So 80% approximately. And just keep in mind that those little squiggles right there, every now and then I'll have a student ask me what that means. That means approximately, all right? Because the exact answer is, very, very difficult to find, because you can see this is what we call an irrational number, because calculators and computers are going to go out as far as they have the memory to hold, but these things have to be rounded off someplace, and when they're rounded off, then there's going to be loss of accuracy. So that's when we say approximately. Like if you have 3 and you write it as the square root of 3, that's the exact value. But when you evaluate it, it's going to have to be an approximation. Okay. If you evaluate a particular decimal place, it's going to be an approximation. All right. So let's just look at the properties that we've looked through. Log b of 1 is always going to be 0. So this is just the general properties for the common logarithm. Log of 1 is equal to 0. Log b of b is just going to be 1. So log 10 of 1, because 10 to the first power is 10. Here's those inverse properties. So log b of b to the x is just going to undo one another and get the x out. So the log of 10 to the x power is just going to give you the x. Working the opposite way, base to the log b of x is just equal to x. These parts undo one another. So 10 to the log of x is equal to x. Now, the last thing is what we're talking about is natural logarithms. These are going to be the most useful ones for applications. Not all applications, but generally things in nature mimic very well the movement of natural logarithms and exponents. So, as I had said before, you won't see it written as log e to the x. You won't see the e. What they'll use, just like they did here for the for this, these all mean log 10, base 10. But if it's just plain log, then it means base 10. That's just the convention. So over here, rather than see log base e, you would just see ln, which means natural logarithm. So the properties then adjusted for the natural logarithms, or this is the general properties. We already said that on the other side. So the equivalent is ln to the 1 is equal to 0, as all logarithms will be. Ln to the e, so what we're doing is, this is ln or log base e, which they undo one another and just give you 1. Here's those inverse properties. Look how it's a lot shorter when you're dealing with the logarithm, like the natural logarithm or the common logarithm. So ln of e to the x, the ln undoes the e, and you just get x. And then e, the opposite, the exponent of the natural logarithm of x is equal to x. They would undo one another. All right, we'll look at one more application. Anybody got any questions? All right. All right, so just in case you came in, remember, we're finishing up chapter 4. We'll have a test right before Thanksgiving. Like I said, I like the idea of having just a couple of days off before we come back and just review for the final exam, which covers everything. All right. So, and just, so the grade, remember, grades are maintained in Canvas, nowhere else. Now, for the end of the class, the final grades are to go in low, all right? But you should have everything that you need to know what your final grade is in Canvas, all right? Just remember that, because it puts me in a position, a crazy position to, if somebody emails me and asks about grades, I'm really not supposed to do that. So everything should be in Canvas to let you know what's going on. And remember, this is why the dates are important, okay? Remember, at the end of the semester, which we got shifted a little bit because of the hurricane, all right? This is when the exam is. I'll probably open it up like a day early for you, and then have it open on this day if I can. I think that I will be able to do that with this class. So that means that I've got to have a deadline of Friday to get these grades in. So just remember that, because this is where we got a hard and fast end of semester, no more time to fool around thing, okay? Keep that in mind. That's very important, because invariably I'll have somebody, contact me a couple of days after the exam, come in on Monday to check things, to get everything figured out. And, oh, I missed the exam. Well, it gets really difficult then. If you're just missing like an exam grade, then I'm going to say, well, we'll just wait till the next semester and do an incomplete, because, you know, we don't have much time now because we extended that semester. So some of us want to get out of town and be finished with this semester from hell. Okay, keep that in mind. So if you got any problems, let me know beforehand and I'll try to work with you, but don't, you know, take those things for granted. I mean, I've tried to play a little bit loose with the due dates as I could on each of these tests, but you know, the exam, I don't have that freedom. So let's get back over here. All right, so here's another application. When the outside air temperature is anywhere from 72 to 96 degrees Fahrenheit, the temperature in an enclosed vehicle climbs by 43% in the first hour. Now they give us a function that models that temperature increase. All right. They've given us all this information and then they give us a function. So we really don't need to know all this. We just know that the outside air, the temperature in the enclosed vehicle is going to be modeled by this. All right. In degrees Fahrenheit after X minutes. So however X minutes is, you know, 10 minutes, 20 minutes, or whatever, we can put that in here and then figure out. So use the function to find the temperature increase to the nearest degree after 30 minutes. So this is our X. Okay. So X is going to go in the logarithm spot. And again, I'm going to show you how I would evaluate this with a calculator, or if I was writing it down. Now, I'm going to have to use a calculator. There's no way around it. Back, you know, years ago, before calculators became prevalent, they'd have a bunch of values in the back of a book, like a table. But you know, now I don't even know if they have that. So you're pretty much going to have to need to use a calculator, and most any scientific calculator will work. All right. So what I need to do is evaluate this first. So I'm going to put in 30. And then I hit ln this time because it's the natural logarithm. And then I'm going to multiply by, so I would write that down on my paper. I wouldn't just, personally wouldn't just rely on the calculator, because I was helping my daughter with some stuff last night. She's taking physical science, and I was punching things in the calculator without writing them down. And I said, look, this is what I want people to get, because the calculator, when you punch things in, especially with like one like this or one with that's on a phone, you can't necessarily rely on what you press to be pressed, like on a calculator, an actual calculator. And this is why Delgado has, you know, a calculator policy about a specific one. You have a button that you know what generally when it's pressed. Now, unless it's broken, it should press when you press it. So remember, it's important to write these down and always go a little bit beyond. Like I said, I would go 3.401, write that down, and then multiply that by the 13.4. I'm working my way on the inside out. I would write that down and then subtract the 11.6. And see, that gives us 33.9, which is approximately 34. And this is degrees. So after 30 minutes, we would expect that the temperature inside of the car would be 34 degrees. All right, any questions? Let's go to the board and I will go through something from the back of the book. All right. You need that. All right, and I need to actually have the book. Oops. I still got those open. All right, let's go over here. All right, so I'm gonna go over to the book and see the instructions over there. I've got the problems written down here, but I want to see the instructions so you can see them. So this is 4.2. No, I'm sorry. I wanted to go to the book, actual book. It's the same kind of things. I just like to use the book if I can to do things on the board. So we'll go to the back of the book. So this is all pretty much the things that we were looking at on this, and it's just kind of condensed, essentially. And this is the instructions they give you to follow what I was telling you. See, they gives you some basics on how to do this in any calculator. All right, so let's say the instructions here are right. I don't think they let me copy this. Because I remember. Nope. Write the equation and equivalent exponential form. All right, so what I've got here is, this one is like number 8. I've got log to the 5th power 125 is equal to x. So what is x going to be? Well, let's just look at it from the log. Well, we don't need to evaluate logs of what x is. We just need to write it exponentially. So this is the power, okay? This is what the exponent is going to end up being, and this is the base. So 5 to the x power is equal to 125. So if we wanted to evaluate it, then it would be 3, because 5 times 5 is 25, and then the third to 5 gives us the 125. All right, let's get another good one. We got a little bit of time here. All right, 5 is equal to log b 32. So it's number 5. So again, this represents the base, and then the other side of the equal sign is the power. Next section. Write each equation in its equivalent logarithmic function. All right, so I got this one. It's number 20. Eight to the y power is equal to 300. So again, we've got the base. So this is going to mean log base 8 of y three. Oops, I'm sorry, back up. Of 300 is equal to y. In other words, it's equal to the power. The logarithm is always going to be on the other side of the logarithm is the power. All right, so let's see. All right, I got, let me find it good. I thought I had another one here. Because we want to go from the power side. Oh, I'm sorry. Back up on that. Yeah, let's see. Let's do 14. I'll do that over in a minute. Okay. The cube root of 64. All right, so we have to go ahead and write this exponentially. So this is 64 to the 1/3 power is equal to 4. In order to do that, you really should see it as an exponent, unless you can make that adjustment in your head. But anyway, so now that we got that, so we got log base 64 of 4 is equal to 1/3. All right, so it's just a matter of putting them in the right spot. Let's see here. Evaluate without using a calculator. All right, so all right, so we got, this is the one I was going to do 32. So what was it? It's log 3 of 1/3. Log base 3 of 1 over cube root. I'm sorry. All right. So let's kind of evaluate this. All right. So what we've got is, this is the base 3. And we're going to have something here we got to figure out what it is. That's equal to 1 over the cube root. Or another way of looking at it is, there should be an arrow because there's only one equal sign. We're looking at equation. Okay. So what we've got is, if we write this as an exponent, it'll be a little bit more clear. Remember, this right here is, well, let's back up a little second. I was trying to put an intermediate step in here. Okay, for first of all, the 3 gets on the bottom and it gets a cube root. Remember, the cube root of 3 is equal to 3 to the 1/2. All right. And then the other thing, to get it in the denominator, in other words, 1/3 means 3 to the -1. All right. So we got 2 things in play there. We've got the cube root, which is 1/2. And then we've got the -1 there. That's a -1. So this is going to be equal to, let's back up a little bit on that. I don't need to have that again. So what does that mean? That means x has to be -1/2. And that's because 3 to the -1/2 would essentially give us that 1 over the cube root of 3. Because remember, the cube root of 3 is the same thing as 3 to the 1/2. And because it's in the denominator, it's also doing a -1. All right, let's move on to something. All right. All right, let's just kind of look at 47, 48, 49, and 50. They're asking us to line these up with which is which. All right, now remember, the exponent function, let's remind ourselves what it looks like. Okay, that's the exponential function right there. Remember, it's got no x asymptote. The logarithmic function has an x asymptote. All right, so back over here. Then 47. So this one right here. All right, let's just do it a little bit. Okay, which one of these? So this one right here is shifted 1 to the left, okay? See that -1? So it shifted 1, I'm sorry, 1 to the right. All right, so g of x so how many we got here? We got 1, 2, 3, 4, 5, and 6 for 4 of them. There's none. Okay. So I don't see this one here where it's just this one. We're looking for this one shifted 1, 2, 3. I don't see that one. So we could take that one out of the mix. It's not there. Log 3 of x. That's just a plain old one like this. All right. So that's just a plain logarithmic function here. So 49 is this one here. So that's just a plain logarithmic function. We can tell that it's logarithmic because it's got the x asymptote of 0. All right. Now this one right here is the negative of the one that we just identified. Okay. That was not there. So it's the negative of this one. In other words, it's flipped down. In other words, if we would take it a negative wise, we would just kind of pull that right arm down so that it's going down instead of up. So I don't think that one's in there either. I don't see it unless it's that one. No, it's not that one. So I don't see that one in there. The logarithm of 3x minus 1. Now this, the shift is not on the x, it's on the y because it's not inside the logarithm. So this is the logarithm function here shifted down 1. So that would be this one. So this one is 49. All right, so the negative one of that's that one, blah, blah, blah. Now this right here is essentially saying the downward shift went over 1. I want to do one more application. I didn't know this was going to take so long. Let me just go ahead and graph them for you. That'll be the quickest thing. I don't want to graph them by hand because that takes too darn long. So I don't see this one right there. Where is that at? Well, let's zoom in and see. So essentially what you, that's what you do is just to graph each one of these and then see which one it is. And you know what? That's this one right here. So this is H, big H of X. All right. I wish I could write on there. So I'm going to do one more application. I know that last time I didn't get to the last application. The applications are usually the easy thing though. All right. And then my computer is slowing down. Good thing is I'm going over to that new office at the end of the semester and actually have a new computer and everything, and hopefully everything's going to be moving faster. This kind of thing that always happens when I'm trying to rush. The application I was going to do for you is basically just the one that we just did. So let's just take our time on this. So H of X is equal to, what is it? 47. Number 47. So graph another one. Log 3 of negative X. That's going to create the that creates the shift downwards. I mean, it's the flip, okay, across the origin. And that's number 48. So this one is number 48. And what was it called? Let's see. So G of X so like I said, if I was doing this homework, I would be, graphing them basically by hand or whatever, but let's see. Now this one right here is just going to be the inverse. So negative log 3 of X. I'll put X, not 3. So you gotta get the scalar right. So that one is going down through here. That's the actual log that's flipped up. It's kind of flipping up on the y-axis. I'm sorry, the x-axis are flipping up. So that is number 50. So that was f of x, big F of x. Big F of x. All right, number 50, let's see. And then log 3 of x minus 1. All right, do we have that one there? It goes through 2. And again, if you had evaluated several values, you would know that. So that one I don't think is in here. Nope. So that one's not in here. Oh, I'm sorry. That's actually g of x, little g of x. It's not in here. And then that's the h of x. And that's number 49. That was 8. And that's all we're going to need to do because the other ones, we got all 4 of them identified. All right, well, sorry about that, but I wanted to go to an application, but like I said, the applications are pretty much all the same in here. All right, if you got any questions, stick around, let me know. Otherwise, I'll see you Tuesday or Thursday, and we'll hit 4.4. Okay.